Okay, all right, then let's get started. So, welcome everybody to the last One World Probability seminar of the winter term. So it's a great pleasure to have Alessandra Cipriani and Wioletta Ruszel here speaking about fermionic structures in random lattice models. So, Wioletta, stage is yours.
Yeah, thank you very much for the invitation, Peter and Dominic, and it's a great pleasure to be able to speak here with jointly with Alessandra. So I will start, and we divided the talk into two parts. So I would give a brief introduction and tell you what the abelian standby model is and define it, and also what the uniform spanning tree is for those who don't know. And then I will show you on an example how the burning bijection works. So Dar's burning bijection is an algorithm which is linking the abelian sandpile model and uniform spanning tree in a bijective way. And then I will start to give you like an introduction to Grassmannian calculus and give you some examples how to compute with the generators or the fermions. And so this will conclude my part, and Alessandra will then pick up from the setup of the Grassmannian algebras, and she will define the main object, namely the fermionic Gaussian free field. And okay, recall you, of course, what the Gaussian free field is. And this object will be the link, the mathematical physics link to some observables of the abelian sandpile model and uniform spanning tree, which I will talk about in the first part. And then she will present the main results and give you some examples on classical results on the weak limit of a degree of a uniform spanning tree in a complete graph using also the fermionic approach. And she will conclude with final remarks. And please, if you have any questions in between, then ask them. Okay, so let's start. So let me just tell you a few words about the abelian sandpile model. So the abelian sandpile model was introduced like in the late 80s as a toy model by Beck-Tang and Wiesenfeld. So toy model which displayed self-organized criticality. So and then so that time like self-organized criticality like was very, they were very excited about that because so they called physical systems self-organized critical if in some sense they drive themselves into a critical state which is characterized by power laws of some correlation functions, for example, or some other observables without fine-tuning any parameter. So this power laws typically arise in physical systems around the phase transition point, which you obtain if you tune like the inverse temperature or some other parameter. But in these models, you don't tune anything. So in some sense, these power laws arise naturally without any fine-tuning. It is a very rich model. It has a lot of nice connections to, for example, spanning trees, which I will explain in a minute. Also from group theory to abelian groups and Tat polynomials. In the computer science community, it's also known as the chip firing game. And also, which is interesting for us, and which is also the basis why we will connect it to the fermions, also to some log conformal field theories. So let me, before I start introducing and defining everything, let me give you a very simple example. So let's take a subset lambda of the square lattice, let's say, and like this is here denoted by the box. And each vertex in the lattice, to each vertex, I'm assigning a natural number from 1 to 4, which is representing the number of grains or cent grains, if you wish, on each lattice point. Now here, I didn't draw the edges, but just imagine that between the vertices, all the vertices are connected by, so all the vertices have 4 edges, and this box so this outside box represents the boundary, and all the boundary vertices are connected to the boundary. So here in the on these sides with 1 edge, and here in the corners with 2 edges. So this vertex is connected with 2 edges to the boundary, this with 1, 1, 2, etc. Okay. And now so it's a dynamic system, and the dynamics is defined as follows. So I'm picking a site uniformly at random. So for example, this one, and I'm adding a grain to it. So the number of grains will now increase to 5. And the toppling rule is as follows. So if upon adding a grain, the configuration, so the height on vertex is larger than the number of neighbors, which is 4 here, then I call the site unstable and the site is toppling. So here the site get 1 grain became unstable because the height is 5, and will topple by distributing 1 grain to each neighbor, so in all the directions, and then reducing its height by 4, right? So here this site becomes or has only 1 grain left, and those sites will increase the number of grains by 1. And you see the toppling of this site made these 2 new sites being unstable because the height is now 5. Okay. Now, what happens further? So we continue the procedure until we obtain a configuration, which is again, where again, all the vertices have heights or have 1 until 4 particles. So I have to topple now these 2. And you see the abelian, the sample model is called abelian because now you can ask yourself, oh, but if I topple this vertex first or this vertex first, will the configuration be different? But no, so I can topple in any order. I can topple in the same at the same time. The resulting configuration will be the same. And this, so then, okay, again, here, this guy will distribute 1 grain to the neighbors, but this is a boundary vertex. So 3 particles will be distributed inside the box and 1 will leave the box. Okay, and this is important. So the boundary is important because you can imagine, oh, if I put a grain here, the toppling can continue forever. But since I have a boundary, I know that at some point it will stop. Okay, so here I have these 2 unstable vertices, and the border acts as a sink. So I toppled like this one first, and you see, oh, then this guy became unstable, and here this vertex is linked with 2 vertices to the sink or to the boundary. So upon toppling, one grain will be distributed here to the right, 1 to the south, and 2 will leave the system. So either 2 in this case, or here 1 grain will always leave the system. So I continue, and at some point I obtain a unique stable configuration, again consisting of numbers between 1 and 4. And here, just to show you, so we remember we added a grain here at this vertex, and so upon adding a grain at this vertex, I created an avalanche of these blue sites which toppled. Okay, so this we would call like an avalanche of size 5. And it can be also that the same vertex is toppling again. So this avalanche so the vertices involved in the avalanche can topple once or several times. Okay. All right. So let's continue with the definition. So generally, just to set some setup, we will work with subsets of ZD, and then also Alessandra will present some results for the triangular lattice later. But just imagine always that lambda will be a connected subset of ZD, finite, it's also important. And the discrete graph Laplacian is just defined in the usual way. So on the diagonal, I will put -2D, the degree, and on the off diagonal, I'll put the 1, otherwise 0. Note that this matrix is positive definite. And just to remind you, so the discrete Green's function with directly bounded condition is just defined as the solution of this equation. So this is the delta UV, and for all V in my box, and outside I put 0. This will be important also later. Okay. All right. So now we have introduced so the setup. So let us I would like to explain to you how the burning algorithm is working. So let us consider here configurations. This is one stable configuration of, like in a squared box, let's say. And the DAS burning algorithm gives me a nice bijective way to pass from a configuration. In the end, I will obtain here, you see a spanning tree for the wired, so this boundary, so the box just represents the sink, so the boundary. So you have to imagine this, if you would draw it as a tree with 1, 2, 3 degree 4 at the roots. Okay. So I want to pass from this configuration to this spanning tree, and I also can go back. So this gives me a really beautiful, really natural way to have a one-to-one correspondence between every configuration, okay, like special recurrent configuration I will talk about in a minute, and these kind of spanning trees. All right, so how does it work? So in the first step, we burn all the connection to the boundary. So remember, so this was like a wired box. So in the first step, we burn the sink and all the connections of the vertices to the sink. And here we draw the corresponding spanning tree, okay? And then we consider all the vertices which have a height which is larger than the number of existing degrees. So remember, I have burned all the connections to the boundary. So the degrees inside the box will not change because those I did not touch, but I have here, I have burned here one connection. I have burned here on the corners 2 connections, 1, 1, 2, etc. So these corner vertices have now have only two edges, so degree 2, and these like here on the boundary, but not in the corner, they will still have degree 3. So here in the box, there are just I have put the vertices which apply to the rule, so which have height which is larger than the existing degree. Because here the degree is 2, I have height 4. Degree is 3, I have height 4. Degree is 2, I have height 3, etc. So in the first step, those will become what we call burnable. And we burn those 4 vertices, and we connect those vertices to the sink, because the sink will become now the root of my spanning tree. Okay, now you see, okay, in like in this case, it's easy because I can just connect it in one way. There's only, I have burnt one edge, so I can connect it in one way. But all the corner vertices, they have 2 possibilities to be connected. Like here, for example, to the east or to the south. Here to the north or to the west. Here to the south or to the west. Okay. So for this, I have to make a choice, and I have to remember the choice when I'm encoding the spanning tree again to get back my configuration. So for example, here I have 2 choices, but note that, well, for the corner to be burnable at the first time, I know that the height has to be either 3 or 4, because otherwise it would not be burnable. So I only have 2 choices, and then I can make, for example, say, oh, I'm looking at like a like a clockwise ordering. So the first so this is like the lower height. So the first possibility, for example, starting from here to connect this is to the east. So I'm connecting it, to the first possibility. Here, the first possibility is to the south. Here, I don't have a choice. And here, I have to take the second possibility because this is higher than this. For example, you can also, think of your favorite rule, but the important thing is that you have a unique rule, which you remember when you encode that. All right, so I have connected in the first burning time, the 4 vertices. And now I continue, you see, okay, and then, so I burn them, and I burn all the connections and all the edges, which is, emanating from those 4. And then in the second step, for the second burning time, you see those 3 will become burnable because though, like this guy has degree 2, degree 2, degree 2, and before they had degree 3. So before they were not burnable, but since I burned this connection, this became burnable, this and this as well. So I will burn these 3 vertices, and I will connect them to the vertex in the spanning tree, which caused them to be burnable. Okay, so this guy caused this vertex to be burnable, so I connected, oops, sorry. So I connected here. This guy caused, and this guy caused this one to be burnable, so I connected here, this one, etc. Okay, and then I go on. So I connected those three. And then I have those three which become burnable, because here this one has height 4, has degree 3, this one has degree 1 and height 2 and 3, etc. So I continue until I have here one left, and this has height 1. So this is the last one which I'm connecting here. Then I'm obtaining a spanning tree. Yeah, questions about the...
So the last one would not be burnable, but you just connect it.
It would be, because it has degree 0 and it has height 1.
Yeah, okay.
Yes, thanks. Good question. Okay, and then, if you want, you can also go back, but you go back like from the sink. So you see, oh, those were connected to the sink in the first burning time. So it means that, those would have had height 3 or 4. And oh, I connected it here to the first possibility. So this guy had to be of height 3, here height 3, 4, and 4, etc. So, and then you can, like iteratively go back and then reconstruct this thing. Yeah, I think I noticed I missed this one, no? I think I missed this, so I skipped this slide. So let me go back to the slide. Okay, so this was the burning algorithm, but so let me just give you like this definition. So configuration, which I explained before, is just it's a collection of heights. So to each vertex, I'm assigning a natural number, and I'm calling it stable if the degree, so if the number of particles is smaller than the degree. So in my example, I had degree 4, so the heights were between 1 and 4, and then I would call them stable. And then remember, I explained it as a dynamical system. So first I'm adding uniformly at random a particle, and then I'm toppling according to the toppling rule by giving each neighbor like one particle. So this model defines naturally, can be naturally described by a Markov chain, where you're hopping from one configuration to the next with some probability, some transition probability. And then, so using this description, you can prove that there's a unique stationary measure attached to it. Let's call it mu, which will be the uniform measure on the set of recurrent configurations. Because, so remember, this is, so all the, so you have like a degree to the lambda stable configurations, but if you let the Markov chain run, you can split them into recurrent and transient configurations. And what will happen is that the system will concentrate on the subset of recurrent configurations, which is a priori much, much smaller than the whole set of stable configurations. And so this we will use. And also, just like a remark that, from like group theory and number theory people, they really like to look at it from group theory point of view. And like, so the set of recurrent configurations are, together with the addition operation, which is just telling you, oh, I'm adding 2 recurrent configurations, I'm doing the toppling, and I'm getting another recurrent configuration, forms an abelian group. Okay. Right. So, okay. So since I can describe the system by a Markov chain, and so what all I have to know in some sense is the uniform stationary measure on, so this stationary measure, which is uniform on the recurrent configurations. That's why I want to find a good way to describe all these recurrent configurations. And how do I do that? By these burning algorithms. So note that this is not as well, this is also stable configuration, but in particular, this is a recurrent configuration. Okay. And the recurrent configuration, for example, is also characterized by the fact that you have a burning algorithm. So you can apply the burning algorithm and you get a spanning tree. So if you take any stable configuration and you apply this burning algorithm, then you might get stuck, and then the configuration is not recurrent. Okay, so this fact you're using because, well, if you know the number of recurrent configuration is equal to the number of spanning tree, and I know that, well, how can I compute the number of spanning trees for some graph? Well, this is just a determinant. Then I automatically have that, oh, the measure, so the mu for, like, let's pick one configuration, the mu of this configuration can be computed by 1 over the determinant of the Laplacian. Okay, so if I want to, so it's true that it is a dynamical system, but if you want to describe like avalanches and like all kind of observables, we always put ourselves at stationarity. So we evaluate those things at the stationary measure with respect to this quantity. Okay. And then you can ask yourself, well, so I have showed you in an example what happens like for Z2, but well, you can do, maybe you can ask yourself, oh, what about stationary measures for if you let the lattice size go to infinity? You can ask yourself, oh, if I take all kind of other graphs, trees, random graphs, whatever, how does this measure behave? Can we say something about the avalanche sizes? Because the avalanche sizes, they follow the power law distribution. So this is one of the observables where you got the power laws popping up. So if, showing also the self-organized criticality, and also for the 2-point correlation functions, power laws popped up. You can look at like all kind of variations of this model. Like for example, this divisible sandpile version where you don't have a sink, but you just yeah, you define like a random configuration, and then you topple, and then you see what comes out and how much each vertex is, for example, toppling, how much mass it's emitting. This is, for example, captured by this odometer function, which we have also studied. You can look at scaling limits of this odometer functions and get very nice random interfaces popping up. So there's a lot of nice, interesting analytical and algebraic questions attached to it. Right, so another theorem or property which will be interesting and important for us is the Burton-P-Mantle theorem. Which says the following. So if I have a spanning tree, then the probability that some set of edges, let's say E, is a part of the spanning tree can be computed by the determinant of this transfer matrix M. And the transfer matrix M is just the double, it's defined as the double discrete gradients of the Green's function, which I've introduced before. Okay. So this gives you a nice relation between, okay, oh, certain edges of, which is present, so fixed edges present in a uniform spanning tree, and the double gradients of the Green's function. All right. Now, let me remind you what how to compute cumulants, and then I will pass to the Grassmannian calculus. Yeah, so remember the cumulant generating function for, like, let's say vector x1 to xn is defined as the logarithm of the expected value of e to the t times x. So t is a vector, t is a vector, x is a vector, and it's just given by this formula. So computing cumulants is in some sense equivalent to computing moments, and for us it will be more convenient to work with cumulants. And we will look in particular for joint cumulants of the vector of order 1, which are defined as follows. So I have, let's say, x, like n different variables. So the cumulants of these n different variables, so the joint cumulants, can be just computed by taking the nth derivative in all the n points of this function. Okay. Well, easy examples. If n is equal to 2, so I have only 2 random variables, then this is equal to the covariance. And if n is equal to 3, so the cumulant between 3 different random variables is just the expected value of the renormalized, renormalized, let's say, product of this xi's, xj's in x case. So I'm removing the mean here. And let me just remind you the formula for passing. So this is just a cumulant of xi, where I is in some set A. So there's natural formula for going in one direction and the other to express. So if I have here the k-point function for my set of random variables, I can pass via this form. Okay, no, other way around, sorry. If I know the cumulants, no, sorry. If I have the k-point functions, then via this formula, I can compute the cumulants. And there's also an equivalent formula if you have the cumulants to compute from there via some sums over permutations, etc., to compute the k-point function. So it's really, if you want, because in physics also you're really interested in computing k-point correlation functions, but here we just wanted to show that, well, it's the same thing, work with cumulants or with k-point correlation functions, but for us it will be convenient because we are renormalizing, we are removing the mean. Later, if you take scaling limits, this will be useful. Okay, great. Now let me pass to the Grassmannian framework right now. So I just recall we have seen roughly what the Abelian sandpile is, how it's defined, how to pass from the sandpile model to the uniform spanning tree. I've explained to you that it's important to have this bijection because it gives me a way to compute the uniform stationary measure. And if I know how I can compute the measure, I can compute some observables for that. So I can compute k-point correlation functions because they have to be computed using the measure, or avalanche size distributions or whatever. Okay. Right. And now, so this framework will allow us to find an equivalent way to express those cumulants or k-point correlation functions, and then get a bit more physical information, let's say, about them. All right. So remember, lambda will always be a subset of ZD in our case. We will define the following Grassmannian algebra as the ring over the reals generated by some symbols, which we call xi1 to xi2 cardinality of lambda. So we will take, that's why it's important that lambda is finite. So for any finite lambda, we will take twice as many generators to build the polynomial ring. Okay, so if I have 2 points, then I will need 4 generators to build the ring. All right, so what are objects, polynomials of this polynomial algebra ring? Well, so there will be just combinations of, here I is a subset of all numbers. So this is just like, okay, just number your vertices of all vertices 1 to 2 times cardinality of lambda. AI is just a real number which is associated to the index set I. Here I, for example, is I1 to IP. So let's say this is like that. And xi I is a short way of writing the product of xi I1 up to xi IP for this index set. And so this is the important property. So this, the generators of this algebra are anti-commutative, which means that if I'm taking 2 of them, which are not the same, and I interchange them, then I will get a -1. And as a consequence, also you have that the square is 0. It's also called the Pauli principle. Okay. Then let me introduce some rules to compute with these generators. So what we will need is to know how to derive and how to integrate. So derivation in direction xi j of this product is defined in the following way. So remember, I was just the index set I1 up to IP. And this is just the product of xi I1, xi I2 up to xi IP. So if I'm deriving in direction xi j, for example, let's say j is equal to I1, then the derivative is just xi I2 up to xi IP. Okay. If this is like xi I2, so like the second in the list, then I would have to switch, have to make one switch. So then the derivative would be minus, and then xi I1, xi I3, etc., xi IP. And in general, if j is equal to alpha, let's say some index in the middle of my product, I have just to count the number of switches I have to make to bring this monomial to the left. And this is given then by this -1. So this will be just the product of the remaining monomials. I replace the one here, which I'm deriving by 1, and I have just to be careful at which position it was, because I have to count for this in this number of switches with this -1 factor here. And obviously, if j is not part of this index set here, then the derivative is 0. Yeah. All right. So this is derivation. Easy. Oops. Integration is defined via derivation. So this is also called the Grassmann-Berezin integral. So if I have any f, any polynomial from my polynomial ring, then the integral over this thing is just the partial, so this derivation which I defined before, over xi2 lambda up to xi1 of my f. So this is ordered in this way. All right, so let's pass to some examples. Let's say I have 2 points, V and W. So remember, I have to build my ring. I need 4 generators for 2 points. So let's call them xi V1, V2, W1, xi W2. Then possible objects from this algebra can be, for example, just the product of these 3 generators. Easy. If I do any square here, I will always have a 0. So, but this is also, of course, an object. And F3, for example, is, okay, I have every generator appearing. Oops. Yeah, if every generator appearing, and I have here, for example, 3 multiplying everything. And here you see I don't have here the right order. So if I want to have it in the right order, I have to make a switch. So what are derivatives if I take the first polynomial and I'm deriving with respect to the first coordinate? Well, remember, okay, I'm doing it. So I have to count how many switches I have to do to bring the monomial to the left. Here I don't have to do any switches, so this gives me a 1, and those 2 monomials will be remaining. Okay. Now let's look at some integration. If I want to now integrate F1, then I will get a 0. Why? I get a 0 because remember, integration really takes into account all the generators. So if I have any polynomial where I have 1 generator missing, then it will always be 0. So I really need to have a product of all the generators present, which I don't have here. So the integral is well defined, but it's only 0. Okay, F2, it was 0. Anyway, here F3, you remember this had all the generators, right? I have here the number 3, but the integral will give me here a -3 because they're not in the right order yet. I have to put them in the right order, and I ordered them like this is the first, this is the second, this is the third, this is the fourth. And here, to be in the right order, I have to make 1 switch, which will give me a -1. So I have -3, and then the product over all the monomials. So the integral over this thing will give me a -3. Just non-trivial in this case. Okay. Right. Then I need to tell you what to do with if you have an analytic function. and you apply this. So you do like you apply this to your polynomial f, where this is just defined in a Taylor fashion by looking at the infinite sum. Okay, by the infinite sum of some coefficients which we real, and then the sum of all the powers of your polynomial. So this is an infinite sum, but remember that we have that as soon as you have a square, then you're killing the sum. So this in the end for every analytic function will be a finite sum. Okay, examples. If you have, I'm taking, again, I have 2 points and 4 generators. I'm taking here the sum of this generator and this generator square. So my f is just the square, my little f. My big F is the sum of these 2. Well, so if I would just compute it out, I would have like the square of this one, which is 0, the square of this one, which is 0, and then the sum of the terms multiplying each other. So one time you have V1, VW2, and once from another product will give you Xi W2, Xi V1. And well, so if it would be normal bosonic calculation, well, okay, you can switch them. It gives you the same sign. It will be twice the same. But here, if I want to add them up, I have to switch them, the order. But switching gives me -1. So this will give you 0. Now, if I can play this game now with couples, if I do the couples like that, so switching couples, switching couples of 2 fermions makes them bosonic, and bosonic variables are commutative. So in this case, if you look at couples and then the square of the couples, you don't get 0, but you get this middle term popping up, because you had once this product times this product, and another time this product times this product, but then you switch the couples twice, then gives you twice a -1, which gives you a +1, so you have in the end twice this product. And another very important function, which Alessandra will need in a minute, is the exponential function. So here, note, well, the exponential of this fermion is very easy. It's just 1 plus the first linear term. Because if I take my Taylor definition here, well, all the higher order terms will have at least a square, so they will be killed. Right? So the exponential of this fermion is just 1 plus that. And for example, cosinus, if you want to go crazy, so cosinus has, well, the linear term and then all like even powers. So here, the cosinus of a fermion is also just 1, because all the other higher order terms will disappear. All right. Questions about these properties? No.
I mean, maybe this will become clear later, so feel free to just tell me to wait. But what's the intuition behind this calculus? Like, why would you introduce it?
So yeah, so you want to make you want to introduce something which is anti-commutative, because this anti-commutation will give you negative correlations. And you will see that these observables, which we will look at from the uniform spanning tree and the Abelian sandpile, are negatively correlated. Right? So and they can be expressed in terms of determinants, which also will be clear in a moment why. So you have, determinantal structure plus negative, which gives you also automatically negative correlations. And the commutative counterparts, or the bosonic calculus, will give you positive correlations. So you already know, my sandpile cannot be bosonic because it is not positively correlated. All right. Sorry. What we will do now, so I have done implicitly already, like in the example for 2 points, is, okay, so we change a little bit notation. Instead of psi I, psi j, we will consider psi v, psi bar v. So remember, we have constructed the algebra in such a way that it has precisely twice as many generators as points. So it is natural to define per point, so to associate to each point 2 generators. Okay, so here let's say V is just a vertex, a point in my set lambda. So I'm associating to it 2 generators, which I will, okay, before I called them xi, I, xi, j, but I want to call them now psi, psi bar, just to show that that they belong together. And the bar is not the, for us, our generators will be real, but the bar is, yeah, it's mimicking something like, you know, convex conjugate in some sense. So that's why the notation came about. And so the integral, if you now have your set of 2 cardinality of lambda generators, you know, you put half of them, you call half of them psi, half of them psi bar, then your integral, which remember was just so was the derivative with respect to now all ordered pairs. I want to make it now the integral over, I'm taking all the psi indexed by the vertex set lambda and psi bar indexed by the vertex set lambda, and defined it as, you know, the product over, this is just, let's say lambda has the ordered index set 1 to n. So I'm taking the product over all pairs of psi bar I, psi, the derivative with respect to psi bar, derivative with respect to psi I of my polynomial f. Okay, you can also do it by, you know, first all the psis and then all the psi bars, but then this will, with respect to this, will just change by a -1 sign, because you have to make a certain amount of switches. And this is the important property which Alessandra will use in a moment, which is very important, namely the following. So take any matrix A, then look at the inner product between the, so this is the vector psi indexed by 1 to n. This is the matrix, which is n times n. This is again psi bar, a vector of size n. So you have here, so you take here the inner product, which will be then one-dimensional. You take the exponential of that, which I showed you is defined via this Taylor sub-expansion. And remember, which will be in the end the finite sum. And then you take the integral with respect to this n-dimensional vectors. Then this integral, so it's also called the Gaussian integral, will give you determinant of this matrix. Okay, and Alessandra will tell you the motivation also why it's also called the Gaussian integral and how it is related with the Gaussian integral. So this will be a bit more clear in a moment. But what is important is you keep in mind this property, which is true for every matrix A, n times n matrix A. And that's it for my part. So the story to be continued will be now part 2 of Alessandra.
Yeah, well, thank you very much, Wioletta, for a very nice introduction and very nice talk. So I'm sure there are questions. So feel free to unmute yourself, raise your hand. Or if not, let me maybe start with the first one. So you talked about really the abelian case, but what happens, for example, if you're not equally distributing your particles to the neighbors? And let's maybe say just in one dimension to make things simpler. Let's just say P and 1 minus P.
Yeah, somehow. If you use abelianness, you lose everything, and you don't have necessarily anymore this burning bijection, then the description of the stationary measure, etc. So abelianness is really key to be able to compute things. And people have studied non-abelian models, I think mostly numerically, but like really to say something concretely, it's more difficult.
But even like somehow going down to one dimension doesn't help you, because it seems like there's like a somehow discrete heat equation type of involved, like somehow with your Laplace operation, whereas somehow you can do asymmetric models and you would just go to Burger's equation more or less. So if there, so even going down to one dimension, there's nothing which would help you.
Yeah, there has been some SPD approach by Benjamin Guess and those groups. Not only if Alessandro remembers precisely. So he had like some heat equation SPD approach to like a sandbar. So really looking at it from a dynamical point of view, because we are in stationarity. But if I remember well, he also assumed abelianness. So I'm not sure. Just know that a lot of things like like a lot of properties will not go through. And you cannot say much.
Perhaps one question. So I can't remember if at the beginning you implicitly assumed the dimension doesn't really play a crucial role here, right? You could do this in higher dimensions.
Yeah, we will do this in D dimensions, general D dimensions. Yes.
Okay.
Yes.
Then I guess the more interesting question, how did you call them, avalanches or cascades? Is there some obvious, I don't know, bijection in if you have a starting configuration and you pick a vertex, what the avalanche is going to be?
Yeah, that's a very good question. So the avalanche is like a bit of a holy grail, to be able to compute all the avalanches and to show that when they are have like a power law decay, when they are like critical, right? So what happens is the following. So on a tree, if you have a tree, then you can decompose. So the like first, okay, this you can always do. So you can decompose avalanches into waves. So waves are defined as follows. So you have your vertex where you added a particle. This vertex is starting an avalanche. And then you look at the first time that this vertex, which started the avalanche, becomes unstable again. And this will create again a set of topplings. And this is called the second wave. And then you have a third wave, etc., etc. So you can decompose the whole avalanche into, wave 1, wave 2, wave 3, wave 5 until it stops. What happens on the tree, what is nice, is that the first wave will be the biggest one. So the first wave will contain the whole thing. And the second wave will be subset, the third wave will be again subset, etc. This is not true on the lattice. But there's a very nice, there's another like bijection between like two component spanning trees, let's say, and these waves. So we have a way on trees, tree-like structures, to compute like tails of this avalanche size using this wave construction, but this doesn't work on a lattice. So on a lattice for high dimensions, you can show that it is of power law decay with power law exponent of a half. But for example, in 2 dimensions, it's not known. Not even if if you like the no lambda going to the whole lattice, if there will be finite almost surely the avalanches or not. In 3 dimensions is also not known. So from 4 and higher dimensions, things were known, because the 4th dimension is like the critical dimension, and for 4 and higher, we can estimate that the avalanches will behave of like size to the minus a half, which is also happening on trees. So there we have a nice description. But on trees, it's beautiful. You can have this you can have this nice construction, and you have this wave description, which will give you the full information of the avalanche.
And I guess in dimension 4 and above, you kind of use that at large enough scales you're tree-like, or?
Probably. I don't remember the details of the proof, but probably this will also enter.
All right, thanks.
Right. Any more questions from the audience? So doesn't seem to be the case. So thanks, Wioletta, again. And we're making like a 3-minute break and then continue with Alessandra. Oh, perfect.
So I hope it's
Yeah.
working.
Yeah.
Yeah, it looks very good.
Let's maybe hide the video.
So,
yeah.
Try to do it like that. Try to go slow so that I hope it's syncing well. People can read and see.
You want to minimize the Zoom window down there, or
probably.
The iPad.
Can I do that? Yes. Hope it's gone now. All right.
Cool. Yeah, looks very good. Then, yeah, I guess we can continue. So, yeah, welcome back, everybody. So it's a great pleasure to have Alessandra Cipriani giving us like the second part. So
Thank you.
Here you go.
Thanks, Dominic. Thanks, Peter, again for also from my side for the invitation. So I have this big job now. Wioletta was explaining to you, or was giving you somehow a sort of a list of toolbox, or a list of tools that we would like to use in our analysis of these lattice models. And these models probably do seem kind of unrelated from one another. I mean, we saw that there is a connection between the sand pile and spanning trees, but perhaps it's not so clear what's going to happen, for example, with Grassmannian calculus, with cumulants. So let's try to go into that and let's see what happens, how these models or how these tools are related to one another. So for that, I have to apologize because I have to introduce to you yet another model. And this model is a very famous one in statistical mechanics. It has a slight relation to what I'm going to say later. If you have never heard of it, then you should just think that I'm going to talk about a Gaussian vector. Nothing more complicated than that. So I'm going to define now a Gaussian vector on lambda, or a finite connected subgraph of ZD. And since it's a Gaussian vector, I'm just going to use its mean vector and its covariance matrix to define it properly to you. So this particular Gaussian vector I'm going to use is the discrete Gaussian free field. So the discrete Gaussian free field for me, as I was saying, is simply nothing more than a multivariate Gaussian random variable which is centered and whose covariance matrix is given by a constant multiple of what Wioletta defined as the discrete Green's function. So the inverse essentially of the Laplacian matrix. Of what is a Laplacian? Wioletta said that this Laplacian is positive definite, or minus, sorry. The discrete Laplacian is positive definite. So this is a perfectly well-defined normal vector. It's a model that's being used a lot in probability theory. It has a lot of connections to other models, and I'm certainly been hiding lots of things under the rug now. I'm not describing the DGFF for the time being. But I just want to mention it because I'm going to explain to you how this model can be translated into this Grassmannian calculus setup. So at least for me, Grassmannian calculus is just a different version of the traditional calculus 101 that we study during, let's say, during the course of our studies. It's just a calculus with different rules. And in the same way, I can make probability, I can do probability in the traditional way with the usual calculus rules. I can also do probability with this new Grassmannian or fermionic rules. So if you believe what I said and you say, okay, I have a multivariate Gaussian in the, let's say, traditional world, can you transfer it into the Grassmannian world? I'm trying to describe now how to extend the discrete Gaussian free field, this particular multivariate Gaussian model, to the fermionic or Grassmannian setup. So how am I going to do that? I'm going to define the Grassmannian, or if you want, fermionic, I'm going to call it like this because of these anti-commutation rules. The fermionic sibling of the discrete Gaussian free field as what I would like to call, or we would like to call, the fermionic Gaussian free field. Okay? So how do I define the fermionic GFF? Well, I would like to tell you what expectations look like for the fermionic GFF. In particular, let's say that I have a function f of these variables. Now remember that in this polynomial ring, so I'm working on variables that are actually, I should think of them as polynomials. The polynomials are written in these variables, psi and psi bar. And I'm telling you, well, if I have a function f of these variables, what's its expectation, its mean under the fermionic GFF? Well, it's an integral, again, in the Grassmannian sense, of e to a quadratic form, essentially psi minus delta lambda psi bar, times f. Now, why does this definition make sense? It's slightly different from how I defined or how I introduced the DGFF before, but what I could have told you in the previous slide is that, well, you give me now a function f of my DGFF variables. Probably here there is a small typo, maybe dzen, so the cardinality of the set lambda. But okay, apart from this d, which is entirely probably not consistent with the notation, well, what I mean to say is that if I have to integrate a standard, the classical, Gaussian measure, all I have to do is I have to take the exponential of a quadratic form, which, as you can see, at least pattern matching wise, is really similar to what I wrote in the fermionic sense, times the function f. And then integrate over the variables that define the DGFF coordinates, the DGFF components. So it's same, because you really do pattern matching and see that these two things are similar, but yet they live in two different worlds, where the calculus rules are not equivalent, they are not identical. For example, since I would like to imitate probability measures in the Grassmannian world, what I would hope for is that this integral, without the f, this total integral has finite mass, let's say, has a finite normalization constant. It's such that the integral of the one function is finite. And it's actually true. This is one of the latest rules that Wioletta introduced, that if I integrate in the Grassmannian sense the one function under the FGFF measure, I'm getting the determinant of minus delta lambda, which, as was mentioned before, is a positive number. But if you remember what we do for classical random vectors, Gaussian random vectors, if you do the same for a Gaussian measure, what you're obtaining up to a universal constant square root 2 pi, whatever that I'm forgetting about, you're getting the same determinant, but to the power minus a half. So again, the two things are kind of the two sides of a very similar object, this Gaussian integration that I'm trying to implement. And quickly, to tell you the differences between these two models, I'm going to the setup of, for example, correlations. So as I was telling you before, for the, maybe I should write it here, if I'm interested, let's say, in the correlations, the 2-point correlations between two variables of the DGFF vector, this is going to be proportional to the Green's function at sites I and j, if I and j are two sides of my set lambda, and you can prove that this number, again, is a positive number. If you do the same for the FGFF, again, using a bit of calculus, of Grassmannian calculus, the expectation of psi v psi bar v is equal to g lambda at v. The expectation of psi bar at two different sites, v and u, let's say, is equal up to a constant to the following number. What I'm interested now is in the fact that if, for example, I compute the cumulant, which is the analog of the covariance between psi and psi bar at v and u, what I'm going to get is a strictly negative number. And this goes back to what Wioletta was mentioning before. While the discrete Gaussian free field has positive covariances, is positively correlated, maybe I should say, what we get on the fermionic side is a process which has negative correlations. Why is this of interest for us? Well, because the models, the lattice models we were talking about, are negatively correlated models. So I won't prove this, but you can, for example, prove that the edge probabilities of the UST are negatively correlated. And also, what I'm going to introduce in an upcoming slide is what I'm going to define as the height one field of the ASM. So there are some structures inside the ASM, which are actually the objects we are interested in, that have negative correlations. Very vague explanation, or if you want, a very vague answer to what Peter was saying. Why are you interested in studying these kind of processes in relation to the abelian centpile? And I want to show you that it's not just a matter of correlations that have the same signs, it's something deeper than that. So, before I go on, and this is again a not exhaustive list probably of authors that have talked or dealt with the fermionic GFF as an important object, and not just in probability, but also in physics. So I was telling you, it's not just a matter of correlations having the same signs, it's even more than that. And now I want to come to the relation between the FGFF and the UST. So I have my finite graph, subgraph lambda, and I'm asking you how many spanning trees are there in lambda. So this is the matrix tree theorem. We have seen it already. It's the number of such trees is determinant of minus delta lambda. Now, this should ring a bell because I think either 2 or 3 slides ago, I told you that this number is exactly what I would call the normalization constant of the FGFF. So it's the integral, the entire integral of the FGFF on these variables. So we have now negative correlations. So we have if you want, normalizing constants for the uniform measure on spanning trees of lambda and the normalization constant of the FGFF, that they are the same. Can I go beyond this? Can I give you a more concrete relation between FGFF and spanning trees on lambda, in particular, uniform spanning trees of lambda? So let me introduce now this field, which I call zeta. So zeta now is a fermionic or Grassmannian, if you want, field on lambda. It's actually a field which lives on edges of lambda. So here I have an edge E, and let's say that its endpoints are I and J. So what do? Well, I construct a polynomial, zeta, indeed, which is the product of 2 monomials. And these monomials are the differences, the gradients, if you want, of the variables psi and psi bar along the edge E. So psi I minus psi j, psi bar I minus psi bar j. Okay? So this is a polynomial, which is written like this. If you were to imagine that this bar is really a complex conjugation, this would be roughly the modulus of the gradient of psi, if I think that the gradient here is really the difference along the edges. But this zeta is important from a geometric point of view because it actually tells me exactly the edge probabilities of the UST. So what do I mean by that? So let's say that I give you two subsets of edges of lambda, E and F, and I ask you what's the UST probability, so this is a UST probability, that the edges of E are in the tree, in the uniform spanning tree, and the edges of F are not in the spanning tree, in the uniform spanning tree. Well, I can write this probability as a normalizing constant, this one that I gave you before, but I can encode these edge probabilities as the product of the zetas on the edges that I want in the spanning tree and 1 minus zeta for the edges that I do not want in the spanning tree. So morally, this theorem, which has been proven, in different fashions by these different groups of people, tells me roughly the way I remember this theorem is that the indicator function that an edge is in a spanning tree is morally the zeta fermionic variable. So you see now that the FGFF is encoding or is enabling me to work on the UST. So how does this proof work? I'm not going to give you the proof for this fact. I'm just going to give a proof by example, and I hope that I will convince you with that. So very simple example. I give you 3 edges in lambda, and I want the first one, E1, to be in the spanning tree, and E2 and E3 not to be in the spanning tree. So what's the probability for the uniform spanning tree of this event to happen? So what do? Well, you try to work on that with inclusion-exclusion, and you're getting to this formula here, not very difficult, just inclusion-exclusion. Now, on the fermionic side, what would I have to compute? Well, I would have to compute the fermionic expectation. Here again, I'm discarding for a second the normalizing constant. I have to compute the FGFF expectation of this polynomial, zeta 1 for the zeta along the edge E1. And then since I do not want the edge E2 and E3, I have 1 minus E2, 1 minus E3. Then I just develop this polynomial, and I get an expression that I hope they can fit in the same slide. Yes, in the same screen, sorry. You see that these two expressions are really similar, so all I'm left to do now is in fact to prove that I just need to know when edges are present in the spanning tree to conclude. Okay? So how do I do that? Well, so since I was telling you, I'm trying to transfer essentially everything that I'm doing in the standard, in the classical, I would say, Gaussian or probabilistic case. I'm trying to translate it into this world where you have different calculus rows. And one of the important tools that you have when you work with Gaussian fields, Gaussian variables, is what is called the Wick's formula or Wick-Isserlis formula. So there is a version for the Wick's formula also in the Grassmannian case, and it goes as follows. And it essentially enables me to calculate under the FGFF, again, inverted comma, measures. But it's very general. In fact, it works for any Gaussian measure that I define in this fermionic setup. It tells me, look, I'm making a matrix transformation of the psi variables and the psi bar variables. Here I'm really thinking that psi is a column vector. There is one entry per vertex of lambda. So if I have 2 matrices and I'm trying to make this transformation, matrix transformation of the psis and psi bars, well, I can give you, or I can tell you how to compute it. And again, up to the normalization factor is just the determinant of a product of matrices. Why is that useful? Well, zeta is a gradient, so it's not too hard to imagine that you can find the matrix transformation from the size to the zetas, so from the vertex variables into these edge variables, the zetas, I have just defined. So in fact, there are very two simple and explicit matrices B and C. Actually, one is the transpose of the other, that tell me that I can express the product of the zetas on the edges of the set E as this matrix combination of the size and the psi bus. And how do I conclude? Well, I look at the Wick's formula. In particular, I look at what happens on the right-hand side. I have a good control. I actually know explicitly B and C. And what happens is that if I take the Green's function and I matrix transform it with B and C, I'm getting exactly the transfer matrix. And at this stage, the Burton-Pimentel theorem tells me the determinant of the transfer matrix on certain edges is exactly telling me what the probability is that the UST contains the edges of E. Again, as always, if there are any questions, feel free to stop me. So that's the idea. Essentially, I hope now that you're convinced, well, if I know how to work with the FGFF, I hope I know how to work with the spanning tree. And in turn, via the burning bijection, I hope I can work with the ASM. So one thing that's important to mention probably is that, I mean, it's kind of clear, but better to stress it. The ASM, the UST are very non-local models, right? They have models that have very long range dependence, as Wioletta was talking about before. If I drop a grain of sand at the site of the sand pile, it can cause an immense avalanche that goes very far from where I am, right? So controlling these objects is kind of difficult. We were interested in studying indeed the ASM, and then we said, okay, the entire ASM maybe is too complicated. Let's try to study something simpler. So here, bonus slide that I think I had to add now because there was some notation later on that we hadn't introduced. So apologies to those who have downloaded the slides. In the final version, it's going to be there. So what do we want to study? So Wioletta was telling you that there is a stationary measure. I think Wioletta called it mu, lambda. So there is a stationary measure for the ASM. So now what do I want to study? Well, I don't want to study the entire sand pile. I just want to study where there is one grain of sand in the abelian sand pile in the stationary configurations, okay? So let's start with essentially the first number that we can get in an ASM configuration, number 1. And let's try to see whether we can characterize where those ones align. In particular, we are going to study, and that's why Wioletta was talking about these things before, to characterize these random variables. So we are going to study their cumulants. So we are going to study, for example, the cumulants of the height 1 field at several points in lambda. Again, under the measure mu, just to see whether we are able to characterize this thing, at least the ones. Now, why do we study the ones? Because the UST now comes to our help, is helping us. So Wioletta was talking about the burning bijection before, but it's not the only burning or bijection that you can find between the ASM and the UST. There is actually a particular bijection tailored for the height 1 field. So this particular bijection is essentially telling me, okay, I'm trying to characterize where the ones are for the ASM. Well, this can be translated into a certain event for the UST. what does this event look like? So you ask me, okay, you give me a subset of points V in lambda, and you ask me what's the probability that those have height 1. Then what do I do? Well, first of all, I choose for each one of these points in V, I choose a direction. So remember that everything is on ZD. So I can choose one of the two directions of the 2D directions, one per point. That's my choice, an arbitrary choice. And this is the result. The probability of having height 1 at those sites is equivalent to a certain event for the UST. And for some reason, I prefer not to delve into the formula so much. I prefer to show it with a drawing. Again, very simple example, very simple visualization. So the points that you ask me about, the one where you want to have height 1, are these 3, V1, V2, and V3. Now I chose a direction for these 3 points. I chose in 2 dimensions the east direction. I could have chosen different directions, but different directions per each point, but let's say I choose east for all of them. Then having height 1 means that the uniform spanning tree that you see is wired or rooted at the boundary of my lambda is entering V via my preferred edge, the east one, and doesn't exit anymore. In other words, the UST has degree 1 at each one of these points. So this bijection that I think goes back to Dar and Pritsev, if I remember correctly, and there are other versions, I think, proved by Yaroy and Werning, but it's a classical result, and somehow also highlights the fact that height 1 is easier, inverted commas, because it's a local event for the UST. So knowing whether V1, for example, has height 1 means I have to look at the UST and what it does in the edges, which are incident to V in ZD. And then I can check immediately V1 is height 1 or not, or has degree 1 or not in the UST, and is entering through my prescribed directions. So with that said, I am not going to prove, but I hope I have given you convincing grounds to trust the first main result that I'm going to present to you. And it's this one here. So it tells you the following. Again, I'm trying to look at the event that there is a certain set of sites of lambda. This set is called V, where I have height 1 for the ASM. Well, this is equal to an FGFF expectation. Again, you see the normalization constant here. But essentially, what I have to measure, what I have to average with respect to the FGFF here is a product over V of 2 fermionic or 2 Grassmannian polynomials. And what are these polynomials? So XV is up to, okay, a constant is essentially the sum of the zetas. So X accounts for the arbitrariness, accounts essentially for the direction via which the UST has to be incident to V. And since there is arbitrariness in this choice, because I can choose any one of the directions, then we just say, okay, I choose one direction uniformly. That's where I want the UST to enter into V. It was the red edges that I essentially had in the previous picture. Okay, and that accounts for the fact that I'm forcing the UST to enter V via my prescribed direction. Since I want, moreover, the UST to have degree 1, I don't want any other edge to be present in the UST. So what do? I block those edges. And since I told you that essentially the zeta function is the indicator function that an edge is in the UST, 1 minus zeta is telling me that edge cannot be in the spanning tree. This proof is based on the tools that I gave you before, essentially this burning bijections inclusion-exclusion principle, but I hope that it's reasonable to believe into this result given what I have just presented to you. And let me stress that this result doesn't need to work on ZD only. It actually works whenever you have a finite graph and vertices of finite degree, so where you can tell me which edge you want to choose to enter into V. All right, so this is a nice result. What do we do with that? So we have characterized height 1, and you may imagine that as probabilists, we would like to study limit theorems for these objects. So what do? Well, we try to scale the environment where we're in. So what I'm going to do, and that's the setup of the scaling limit I'm going to present. So you give me a smooth, connected, and bounded domain. Essentially, it's any domain of RD where I have a continuum Green's function. So the inverse of the continuum Laplacian operator. I blow this U up by a factor 1 over epsilon. As usual, epsilon has to be thought as a small number, and then I intersect it with the square lattice or the hypercubic lattice. So again, I always prefer pictures. Essentially, you give me a smooth connected bounded domain. For example, you give me the unit disk U, which is this dark gray area. You blow U up by a factor 1 over epsilon. Here, I think I chose epsilon equal to 1/2. So I get a bigger ball. And then I intersect this ball with the, in this case, a square lattice. So these big black dots that you're seeing here are what I'm going to call U epsilon. And in particular, they will play the role of my graph lambda, where I'm going to play the UST and the ASM game. Okay, where the edges, of course, I should have said that, are those induced by the ZD structure. Okay. Now, I was telling you, okay, on lambda, you remember I have on my graph lambda, I have the ASM, I have the UST. So now let's try to see what happens to, for example, the height 1 field of the ASM played on this particular lambda when I let epsilon go to 0. And what we need for limiting results are limiting approximation of some quantities, so fermionic variables are not enough. Since everything is going to revolve around USTs, I need to have good approximations of M. M is the transfer matrix, which I remind you is what encodes essentially the edge probabilities of the UST. And in particular, we need this result okay, I should probably cite the sources. I think it's proved in a 2D version by Maximilian Dürre. I think can be found in a paper by Cassel and Wu from 2015. And again, apologies if there are more people who prove this result and I'm not citing them. So essentially, what does this result say? Well, you are in this graph U epsilon. You give me 2 points, V epsilon and V prime epsilon. Okay, remember that these points are coming from 2 points that are originally in U, right? So they are what I like to call the blown up discretized version of points in U. And I take 2 edges, F and F prime, which are incident to these 2 points. Then if I consider the transfer matrix on these edges, which are edges of u epsilon, and I rescale the transfer matrix by epsilon to the minus d, what I'm going to converge to is a double derivative. So with this notation, here I mean that I'm taking a continuum derivative in the first entry and a continuum derivative in the second entry of this function here, gu, which is the continuum Green's function. So this is essentially the inverse of the continuum Laplacian operator, the operator that you may have seen in the theory of PDEs. If you have not seen it, I don't think it matters so much. Just believe that there is a very precise limit, and this limit has to do with the discrete Green's function that we have mentioned previously. Okay? Perfect. Now we have this good control on M. What are we able to conclude? Well, we're able to conclude that you give me endpoints in U. Again, think again of the dark gray circle that I was picturing before. You make this blown up discretization. And then you can try to study the limit as epsilon goes to 0 of the cumulants of the height one field, which are related to the ASM that I'm now playing on this graph U epsilon for the blown up discretized version of these points. The first line of this slide is not telling you much. It's telling you that calculating these quantities for the height one field is equal to calculating these quantities in the Grassmannian set framework for the field xy that I defined before. Now, x, I write this shorthand notation. This should be probably x v epsilon, y v epsilon. Allow me to put everything just with one subscript. So I'm using these two fermionic objects, the field x and the field y, to translate my problem into a calculation of cumulants for the fermionic GFF, for essentially fermionic GFF computations. Now you make these computations in the fermionic setup. You use the rules of fermionic calculus. You do use a lot of approximation of the transfer matrix. And you get to a result which is actually the same result that you would get if you had started by computing under the FGFF expectation the cumulants for the field minus c times x, where c is a very explicit constant. We are able to calculate it, as I said, explicitly. So essentially, the first thing that you notice is that this y becomes a correction that eventually plays the role of minus a constant. And what really matters is the choice of how you enter, let's say, into the field V. And okay, why is the result important? It's important also because this limit, so this limit that I'm writing here is a number. It's probably not a very pretty number. That's why I'm not writing it here, but it's a very explicit number. And it's actually matching the results that were obtained by Dürre in 2009 when he was trying to compute the height one field limit for the abelian sandpile when he was working in 2 dimensions. And his proof was very planar, was actually using complex analysis while we are able to extend all these 2 dimensions, which are higher than 2. And not only that, it's not just a matter of squaring the lattice. So I told you the previous result works for finite finite connected graphs with finite degree. So in fact, we are able to do that also for other types of lattices, for the hexagonal, the triangular lattices. And again, we're able to obtain these limiting cumulants in a very explicit way with a lattice-dependent constant. Here, I think there was some software help for the exact computations, but we're able to get those numbers. So you see that this suggests a sort of universality. So it doesn't really matter the structure you're using underneath. Essentially, the limiting cumulants are the same. They are quite robust to the lattice where you're working on. And that's result number 3. Now, in the remaining, do I have 10 minutes?
Yeah.
Okay. So in the remaining time, what I would like to tell you now is, so these proofs, I hope they were believable, but there were quite a bit of computations that I was sweeping under the rug, first of all. And here again, one has to take them. But I wasn't showing you explicitly why or where you need to control the transfer matrix for these type of computations. And what I wanted to do in the remaining minutes is to show you how this approach works and how actually these tools, in particular the approximation of the transfer matrix, are used in a slightly different setup, which as we have seen, is not that different. And that's for the spanning tree, for the uniform spanning tree. So if you remember, I was working with this variable, which I called the xv. I'm writing it here, which is 1 over 2d, the sum over the edges incident to v of zeta e. So if the e's are edges incident to v and zeta e is telling me those edges are in the uniform spanning tree, well, what essentially xv is doing is telling me the degree that v has in the UST. So if I call dv the variable or the fermionic observable, if you prefer this wording, 2d times xv, then essentially dv is telling me how many edges are incident to v and are included into the spanning tree. Uniform spanning tree, I'm always talking about uniformly chosen spanning trees here, okay? So since it was working so well for x times y, does our methodology work just for x? The answer is yes. So if you again ask me, what are the limiting cumulants for these degrees at different locations in U under the same rescaling procedure, we can again calculate the scaling limit, and we can tell you that there is a very precise limit for the cumulants with the same type of scaling factor, and this limit is very, very explicit, which again shouldn't come as a surprise if we were able to do that for the field x times y. So we were doing that for the degree. We would like now, what we wanted to do next was to be a bit more precise on the degrees. So now I gave you the cumulants, or we gave you the cumulants for the degree field. Can we actually be a bit more explicit and, for example, tell you what the probability mass functions of the degrees are? So can I be more specific and tell you, well, the degree in the UST for vertex V is exactly 1, or is exactly 2, and so on and so forth. So in order to do that, I need essentially to repeat what I was trying to do before for the event that I was entering V via preferred edge. So for this slide, EV is going to be the subset of edges of lambda, which are incident to V in lambda. Again, everything is embedded into ZD. KV is what the hypothetical degree in the UST for at V should look like. And XV is the following Grassmannian variable. It's just a sum over the subset of edges of cardinality exactly KV of the product of the zetas on these edges. So now I essentially want to mimic what I was doing before. I want to tell you the UST is entering V in E edges. So it has degree kV given by the edges which are in E, and all the rest is outside or is not included into the UST. And what I have just said in words is written probably better in a more formal way in this line that tells you, well, the probability is that you have a certain degree sequence appearing at different vertices of your graph lambda is the fermionic expectation of the field xkv times yv. It's exactly the same thing that I was doing before for the height one. And again, here, for this result, I should mention it, probably there is no need to really be on ZD. In fact, you just need to be able to count the edges which are incident to a vertex and tell the UST, or if you want, the fermionic GFF, include those, exclude the others. Why is this result useful? Well, because you can obtain useful formulas for the degree probabilities. And this is coming from a paper that Alan wrote after we wrote so I should mention probably that all this was part of Alan's doctoral thesis. What he was computing was this formula for the probability mass function of the degrees. So you can compute out of the previous expression in X and Y, you're able to compute a certain formula for the degree at V being equal to K, again, the degree in the UST. And this is probably not the formula that you would expect by just counting edges in a spanning tree, because if I ask you, well, I wanted the degree at V to be K, my first approach would be, okay, I choose subsets of edges of cardinality exactly K, I place them into the UST, all the rest has to be excluded, while here I have subset of edges which have cardinality larger or equal to K. So where does this come from? I'm not going to prove it, I'm just going to give you, I would say, a plausible example, but again, the proof is in this paper by Alan. Before I go into the proof, let me just say that he actually, so this is a limited version in the sense that Alan was able to obtain a bit more in his work. In particular, he has a version for limiting cumulants of this type of fields, xkv times y. So let me just show you, and that's the last proof second to last proof, probably. Let's see if time allows. So again, let's say that I want to study K equal to 1, which is very similar to what I was doing essentially for the height one field. Well, up to the normalizing constant, if I want degree 1 at V, then it means that I have to choose that one edge that gives me the degree 1, and I have to exclude all the others. So now you know, in this type of things, what do? You expand the product of monomials, and you get to this expression. So this expression essentially is counting over two subsets of edges, the edge E, the edge is E, actually there is only one edge, that is going to give me the degree 1, and all the others that I may have picked up when I expanded the product of monomials, and that's why I get the factor -1 to the F. And then by the fermionic rule I showed you before, I want all the edges in E union F to be present in the UST. If you prefer, that's again inclusion-exclusion. But now, since I have a double sum in E and F, I can transform it into a single sum. I call E prime the union of these two sets. And now you see why E prime has cardinality at least 1. That's the contribution from E. And I rewrite this sum, which was over subsets of incident edges E and F, into a single sum. And when I do so, I'm picking up a factor cardinality of E prime that accounts for the number of ways in which I can create E prime from E union F. And if you compare this formula to what I showed you before, what was in Alan's paper, when k equal to 1, you obtain exactly what I mentioned. Again, this is not a proof, it's evidence, if you want, that this proof or that this result holds. And I'm asking for the organizers to give me probably 2 more minutes. Do I have them? Thank you so much. So here, what I wanted to do next was, as I was saying, to show you a concrete example of the interplay between being able to work with fermionic variables plus the use of limits for the transfer matrix. And why or how can I apply this? Well, I'm not proving anything new here. I'm reproving an old result which goes back at least to Pimentel 2004. This at least is a result if you don't like square lattices, you're going to a different graph. Now I'm in the setup of a complete graph. So you see there is no ZD involved. I have a complete graph on n vertices. And this result, which was, as I was saying, known, proves that the degree of a vertex in a UST for Kn converges in law to 1 plus a Poisson 1. That's a classical result. There is no need to use Grassmannian calculus for it, but you can if you want. So how do you do that? Well, you are essentially required to prove that the PMF, the probability mass function of the degree in the UST of V, converges to the corresponding probability mass function of the variable Poisson 1 plus 1 for all k larger or equal to 1. So you get here. So what's the advantage that you have? Well, on the complete graph, you know the transfer matrix really well. You actually know that the transfer matrix is essentially 1 over n everywhere except on the diagonal where it's equal to 2 over n. So this allows you to make computations much easier. That's why. So as I was saying, you obtain again, or you use the formula that was proven by Alan via fermionic or Grassmannian calculus. That's what I was presenting to you before. Now you use the fact that you know the transfer matrix really well, and in particular, you can calculate its determinant as 1 over n to the number of edges, which are in E, is the subset of edges incident to V, and then there is a factor 1 plus the cardinality of E. You plug this into Alan's expression, and here again, lots of some computations that you have to make. And again, I hope that you trust me when I say that this complicated product that you obtain with the sum of binomial coefficients is actually converging to the right quantity that you were hoping for. So again, here, having a nice expression for the degree PMFs plus knowing the transfer matrix enables you to compute this sort of limiting results. And that's morally what we were doing, maybe in a less convoluted fashion for the height one field. So 3 final remarks taking the last minutes from you and from the organizers and the audience. So the first remark is that I was talking about the DGFF at some point in order to introduce the fermionic GFF. But in fact, the DGFF has a right on its own to be cited in this talk, because there is actually the first chronological result that we proved was that the height field, the height one field of the abelian sand pile has the same limiting cumulants up to a constant factor of what we call the gradient squared of the discrete Gaussian free field. So what we had started with was essentially taking the gradient, the height differences at certain edges of the discrete GFF, squaring this gradient, the height differences, and proving that these height differences in the if we looked at the cumulants, behaved essentially like those of the height one field. And now, in hindsight, this result was not by chance. You can actually reprove this result by using our fermionic result. And the basic, the reason why it's so is because I told you the FGFF and the DGFF are essentially two sides of the same thing. And they are like mirroring each other. So if you're able to pass from Grassmannian to classical calculus and back, that's why we got the first result on the gradient squared of the DGFF. Then, very, very briefly, I want to mention that the fact that there is a fermionic theory behind the height one field is not something that we invented. It's actually a conjecture in physics that has appeared by all the authors who are cited here, who actually conjecture that there is in the scaling limit of the height one, what is called the free symplectic fermion theory. So you see, in a sense, why this fermionic or this anti-commuting calculus is appearing in this context. And finally, perhaps to anticipate a question, I don't know, but I always get asked this question. So we studied height one, you said it's simple, so why don't you make it more elaborate? Why don't we go to higher heights? So the situation there is different for several reasons. A theoretical one, because for these heights, the scaling limit, what is called the field theory behind those heights is supposed to be different. It shouldn't be what we got for the height one field. And from a mathematical viewpoint, the height 2, 3, and so on, under the burning bijection, become non-local events. So to study them, you can't look just at the neighborhood of a point. You need to look at the whole tree to know whether you have height 2, 3, whatever or not. So the situation becomes more complicated, and therefore probably our strategy needs to be rearranged to obtain limits there. So I'm over time, so I've already taken a bit too much of your time, but I would like to thank again the organizers and the audience, and thank you very much for your attention, leaving you with some references maybe.
Yeah, thank you very much for a really nice talk. So we have maybe time for some quick questions. So again, feel free to unmute yourself or raise your hand. I think Peter, yeah, just go ahead.
So earlier, I think it was around theorem 3 or so, you mentioned that, you can do this on other lattices.
This one, maybe.
Yes. So could you also do this on, for example, fractal lattices? So let's say the Sierpinski-Gasket graph, so that one has nice degrees except at the origin. Everything seems to behave as you want it to behave.
Okay, so excellent question. So what I think we need to extend it on graphs is a sort of isoradial property, perhaps. So what we are using in the proof is that these discrete directions are approximating the coordinate directions in RD. So you can do that, of course, easily on the square lattice. You can also do that on the triangular lattice, because essentially all vertices are the same on the triangular lattice. On the hexagonal lattice, it becomes slightly more complicated because you have different, two type of vertices. If you look at an hexagonal lattice, but still you get nice cancellations that enable you to say, okay, I am approximating the RD directions via the edges of my discrete graph, okay? So I think that whenever you have a type of graph that's sort of isoradial, or that sort of where the degree is locally constructed in the same way where you can approximate the directional derivatives in RD, well, then you can do that. I would need to think if this is the case, for example, for Sierpinski. Probably, and here I would be even braver, perhaps you can do that for, you don't even need that. What's the issue? The issue then is that you have to treat the different points in different ways. So you have to tell me, okay, in these points, the directional derivatives are approximated in a certain fashion. Maybe, I don't know, your graph is such that you're weighting the east derivative more than the north derivative because of the way your graph looks like. And in another point, instead, you're approximating the RD derivatives equally in the same way. I don't know if what I'm saying makes sense, but I just want to say you can probably do that even if your graph is not so isoradial, but then you have to work a lot because you have to say, okay, this point is of this type, and in this other point, the derivatives are approximated in this other fashion. So it's just more work.
Mm-hmm.
If that answers the question.
Yeah. Okay, so it's really like this direction that plays a role for you then.
In our computations, yeah, it does.
Mm-hmm. Okay.
Yeah.
Thank you.
So I say one more question, Kalle.
Yes, thank you. So thank you for both of you for the really nice talks. Really nice to meet you virtually. And of course you anticipated almost perfectly the type of question that I might be wanting to ask, and I don't know what is fair exactly to ask in that direction, but yeah, I like really much this identification of the fields in other models with the fields in the fermionic GFF. Now, for the height 2 or height higher field in the abelian sandpile model, that is indeed, there is this exciting conjecture, one of the most concrete conjectures, I think, of relating something to logarithmic conformal field theory. Yeah, I don't know what is fair to ask in that direction. Maybe the simpler question in that direction might be, for the degree higher than one field, you have results, right? And you didn't state, but presumably you could do scaling limit results as well. And maybe the first question is, do they show any need for logarithmic renormalization?
But you mean, sorry, for the higher heights for the ASM?
Yes, I think that's what I'm ultimately interested in. But let's say for comparison, the higher degree, I think you can already control higher degree in the.
So we can control indeed the cumulants for these fields that I called X, K, V, Y, V. Now, if you can explain me again these logarithmic corrections, or
Maybe I can add something.
Sure.
I think for really like matching the fields, you would, first of all, you would need to look at, because we looked at the first joint cumulant and at like K joint cumulants, right? And this would be, looking at, the joint cumulants of the K's power of height 1, the K second power of height 2, all the combinations. And what there comes out, probably some which type of formula for the cumulants which we have now. So this I would expect. For the higher degree of the UST, I think it will be just complicated, but it's still a local thing. So it will be still, I think some kind of a combination of the symplectic fermions. No, but for the higher heights for the ASM, so I'm not aware of a very good one-to-one way to, for example, for the height 2 to be described via some particular properties of a UST. So if once we solve that, then we can translate everything into the edges which are there, not there, and then we can, because the UST we control, but we have to control this non-local events of the height 2, which can have very big range, let's say. But so the translation is as far as I'm aware, not as explicit as for the height 1. Does this answer your question? I'm sorry, I didn't.
Yes, I think that answers the question. Yeah. And to be fair, I think it was very clearly said that the height 1 is much more local in terms of the uniform spanning tree. I was just maybe, yeah. Thank you for the talk, and thank you for the answer.
All right, so I think I see currently no more questions. So let's thank.
Can I ask one question?
Oh, Rasha, yeah, go ahead. Sorry, didn't see any hands.
Sorry, because just to Alessandra, so you mentioned that the physics conjectures are that the scaling limit of these height 1 fields are given by some fermionic variables in the symplectic thing. So what I understood is this: the fermionic GFF is a discrete analog of the discrete GFF in the fermionic world. So is there a continuum analog of the Gaussian free field, like as the original fermionic Gaussian free field, and what kind of properties does it have, if there is one?
Okay, so here an excellent question. So you saw that during my talk I was very careful about, I think I tried not to talk about probability measures whenever I was talking about fermionic things. Because these fermionic variables are essentially thought of as correlations or expectations rather than in the usual way we're thinking about random variables like with probability spaces, filtrations, and whatever. So I know that you can indeed, that on the other hand, you can define Gaussian random variables in the Grassmannian setup. There is a definition that's based on integration by parts. So essentially, you're saying to me that the Gaussian random variable in a proper probability space in the fermionic setup, so you construct a probability space in this fermionic setup, and you can define what the Gaussian fermionic random variable is there using integration by parts. And this is done in a paper by Albeverio, De Vecchi, Gubinelli, and I don't remember the fourth author. Apologies to the fourth author, sorry. But so there are 4 people in that paper. So they define Gaussian variables in this setup. I'm not sure, though, that in their case, the covariance, so they, of course, they need a covariance matrix for this construction. Mm-hmm. And I'm not sure that the covariance kernel of the GFF, of the continuum GFF, which is a particular kernel because it blows up on the diagonal, of course. So if this particular kernel does fit into the assumptions that they have for the construction of Grassmannian Gaussians. So here, apologies, because probably I should have read their paper better to tell you 100% that the GFF can be defined there. But yes, you can define, in any case, you can define, at least to a certain extent, a fermionic or Grassmannian Gaussian variables.
And you believe that this might help in identifying actual scaling limit of the height 1 field in a way?
Okay, my first, okay, probably I should be more educated on the physics side. Of course, I would be interested. Yes, it would be interesting to see what this scales to. So what actually the continuum analog of this object that we are defining looks like, and whether you can define a proper notion of convergence from the fermionic GFF that I presented here to a continuum limiting object. That personally, I would definitely be interested in that. I would also like to know whether this continuum version, if it exists, corresponds to what, for example, you can construct in this Albeverio et al. Setup that they define in their paper.
I mean, from a physics side, there is the symplectic Fermat theory, right, which is the simplest conformability.
Yeah, exactly.
So they have a way to construct it. The question is how to match it from a probabilistic side, probably, right? That's what.
Yeah. Yeah. Thanks, clear. Yeah.
Thank you.
Yeah. All right. Any more questions, comments? So, yeah. Okay. Now it doesn't seem to be the case. So now let's thank both our speakers again.
Thank you.
And because it's like the last seminar of the winter term, thanks again. Like, it was a very nice opportunity for Peter and myself to organize it.
Yeah.
And already as an announcement, the one word probability seminar will continue next term with Luisa Andres and Roger van Pesky organizing it. So yeah, I guess there will be like a couple of weeks break, and then yeah, the new term will start. But yeah, thanks again for
Dominic,
tuning in.
thanks to you for your work.
Well, and of course, like for Peter, like, for all the setup.
You're welcome.
Like the usual. Yeah.
Well, thanks
No,
to the
yes.
organizers. As last speakers, probably we should thank the organizers as well.
All your good
Where's the
work.
flowers?
Yes.
Job done.
Yeah.
No?
Yeah.
Thanks.
Indeed, from our side done. Yeah, Luisa and Roger will then to the organization. Yeah, cool.
Take care,
Yeah,
everyone.
thanks.